In this video, we're going to go through a very light overview of modern extraction techniques to obtain elements from their Earth sources. I encourage you to look through the book and online at various processes for more details on individual processes. In general, what do we have to do to look at a piece of rock somewhere in the world and somehow at the end up with a pure metal? Well, there's a couple terms that have to come up here. Things like ore or mineral. We have to think about what our source is. A mineral tends to be a nice repeating material that has a very defined molecular formula. Various minerals will have some percentage that is, say, copper or iron or sulfur or whatever element you want to obtain. These tend to be very crystalline and are considered a pure molecule if combined of a lot of different elements. Unfortunately, minerals are rather rare. The ready available sources of them have all been found and mined over the eons of human endeavors. The easiest, cheapest source to find an element without any ready contaminations that we don't already know of. And as a result, we've used them. They were the low-hanging fruit of obtaining target elements. Ores, on the other hand, are collections that have lots of stuff. An ore is a mixture of element and contaminants. You might think Minecraft, oh, there's some rock and there's a little bit of something embedded in it, and so you hack out the whole chunk. And that's actually kind of correct. Your ore is going to have all sorts of silicates. It's going to have sand. It's going to have dirt. It's going to have your element, and it's going to have others. It's effectively just hacking a chunk of rock out, and there happens to be some amount of the target element in that rock. Most of the time, this isn't enough that we care about. There's a little bit of gold everywhere. There's a little bit of uranium everywhere. There's a little bit of iron everywhere. However, to make it worth the effort, we need to find concentrations of it. And so ore that is concentrated in one of the elements we want, that's something we have to hunt for. We have to look around various areas and say, hey, there's an area here that's higher in gold. And a lot of times you're talking parts per million for something like gold. But if you can get it high enough over the general amount, you can make it profitable to spend the effort to refine it. When we want to get copper these days, we pretty much have to go to ores. We've been using copper a lot longer than anything else. It was a little bit harder to find and obtain than iron, and all the ready mineral sources of copper have long been depleted. So anymore, we're pulling copper ore out of the earth at a couple percentages, concentrating it up to 12 to 17, and then processing it. Most of the rock that we dig up is not, in fact, the element we want. This means we've got to refine it. We have sources where we can obtain it from, but the first thing we got to do when we have an ore is we need to get rid of the junk, the gang. So your ore contains many things. All the stuff that we don't want is the gang. This needs to be removed. We need to get rid of it so we can work on a much more concentrated source of the element that we're targeting. There's various ways to do this. If you have significant density differences, then you can use tricks like high-pressured air. You have a cylinder, your crushed material is in it, you have some vents at the top, and you blast high-pressure air through. Your particles will go up and then fall back down, but the lighter weight ones will make it to the escape vent. And so you can slowly blast out all the lighter weight materials. And so you would have taken your ore, you would have crushed it and ground it down into a powder, and then you would blast the high-pressure air through, separating out the lighter things, leaving the heavier stuff behind. This is great for heavier elements. If you have lighter elements, that process isn't going to quite work. Other various methods can be used. Sometimes we can leach an element out. If it's particularly dissolvable with certain counter ions, such as chloride, we can use hydrochloric acid to eat a lot of the rock away and dissolve the thing we want. Get into solution and then boil off the water and concentrate down the solution. Additionally, sometimes if you want to extract lightweight things, you put it in oil, you foam it. Heavier particles sink to the bottom, but the lighter particles get caught up in the foam, which you can scrape off, collect, wash away the oil, and then you'll have collected your lighter weight things. There's a variety of methods at this point. It's unique to the source of the ore, exactly what element you're getting, and that particular refinery. So there's various ways that we get rid of all the unwanted material and focus down and concentrate just the wanted material. At this point, we need to turn the element from a variety of possible compounds, ideally into just one. You could have some iron with oxygen, you could have some iron that's got some sulfur, you could have some iron that's got some phosphorus, or you could have copper in various forms, or antimony, or whatever your metal is. It's prone to being combined with multiple different elements at this point. You might be more one than the other, but it's not a single type of molecule yet. Often what we'll do at this point is we'll roast. Heat it up, blast some oxygen through it, and react all the things away that you can react. Turn these all into Fe2O3s. You'll make some SO2s, you'll make some phosphorus compounds. Some of these can be blown away as gas, some of these may have to be leached out or dissolved away with other methods later, but you refine this a little bit. You turn a variety of compounds containing your element, ideally into just one that contains your element, which makes later chemistry much easier because now you have only one thing you have to work with. So after concentrating down to more of just our pure element, reduce the forms of it down to a single one. At this point, we need to get to the elemental form. And so we've taken a large collection of many things, we've separated down to isolate the ones we wanted, we refined it to be just one type of that element, and now we need to convert whatever we've ended up with into the elemental form. In general, for metals, this means we need to reduce it. If we've got an iron or a copper or even a silver salt, we need to convert it into the neutral metal, which means we need to add electrons. For this, we need something that we can sacrifice as an oxidant. In general, sacrificial oxidants are things like carbon, or maybe H2. Sometimes they're more active metals, such as zinc, is used to help refine some elements. Iron especially, using coke, just carbon. In the old days it was coal that could be powdered and crushed up. When this is added, the oxygens will move off of an iron onto the carbon, and then the CO2 gas drifts away. And so as long as your system's set up correctly, you don't have an equilibrium reaction, the redox occurs, you end up with molten iron at the bottom, your CO2 and the like floats away out the air vents, and you can pour out your iron and collect your molten iron. Blast furnaces are their own wonderful modern technology with an insane amount of chemistry based on heat at different distances as the material falls through these incredibly tall towers. I encourage you to look them up independently. There's some great YouTube videos. I am not a metallurgic engineer, so I'm not going to try to go through that in as much detail as you could just freely find online. It's definitely better than the old days where we had to do batches of iron that were a little bit harder. There's a reason steel didn't show up until about 2 centuries ago. It's not exactly an easy process, but the modern world is dependent on it. We moved everything to iron as soon as we were able to reliably produce it en masse. This also works for things like aluminum. The modern electrolytic process for refining aluminum from its aluminum salt requires a graphite anode as a sacrificial agent. Large carbon anodes are dipped into a vat of molten aluminum, fluoride, and other aluminum salts. As a current runs through it, it pumps the electrons into the aluminum and boils off carbon dioxide at the electrode as the carbon takes the oxygens from the bauxite aluminum oxide. So we actually have to make a lot of CO2 to make aluminum in the first place. It's not exactly an environmentally friendly process, but recycling it is. Recycling aluminum is just heating it up. That doesn't take nearly as much energy. It doesn't produce nearly as much CO2. So do make sure you recycle your aluminum. It's probably the best recycling for the environment of all the types that we do. But some sacrificial oxidants used to obtain our pure metal. And so we'll get irons, or we'll get aluminums, or we'll get coppers. Well, we say pure, but realistically, there's still some contaminants in it. There's fluorides or aluminum oxides, or a little bit of carbon that can get into aluminums. Our iron will definitely still have a little bit of oxygen and carbon and sulfur that can get through in the process. And so at this point, there's still a little bit of work to be done on purifying. Once you've obtained the element on its own in a generally pure state, we need to truly purify it. For this, there are various methods. Sometimes we can distill it. Mercury boils at a low enough temperature that we can simply distill the liquid mercury. This allows us to separate it from anything else the same way distilling ethanol from water or methanol from water would work. It's a little higher in temperatures, and you certainly don't want to breathe the air coming out. But as long as you have a good cooling system set up, you can collect the mercury vapor, have it drip down, and you'll have extremely pure mercury. This can work for a variety of lower boiling metals. In the old days, one of my personal favorites for silicon was that we would vaporize it. You'd have an amount of silicon in a system, you'd have a tube set up, and the silicon ions would travel through, and they'd eventually get out here, and they'd start to fall. And they'd pile up, and you get this dome over time. This was the original way of purifying silicon for electronics. You get these big bells of silicon, they'd slice them, and that's how you get these round rings of silicon. This method worked in the early days, but it was a little more messy and brute force, and you had silicon getting up and clogging the system. You had to keep it hot. These days, we use zone refinement. This exploits the idea of crystallization. If you think back to melting point, impurities lower the melting point. And so if you have a solid and it has some impurities, let's just put a few impurities here, and you were to take a ring, a heater element, and you drag it across slowly. And you make sure it's at the temp where it will just be below the melting point of the pure material. Only where that there's impurities will succeed at melting. So as this travels, we're going to see some melting going on inside our solid, just right in that region. Well, the particles inside can now freely move, and they'll bounce around. There's not a lot. And so as they move to a side over here, well, the back side now can refreeze. Without that impurity, it's colder than the freezing point. We're not quite heating it enough to melt the pure material, just slightly under it, so this will start to crystallize. If you grow your crystals slowly, impurities tend to flow out. They don't get trapped in the crystal forming. And so this will cause those impurities to move forward a little bit. Keep moving the ring, this keeps happening. It will continue to melt where there's impurities, and it will crystallize behind where those impurities no longer are. As it crystallizes, the impurities keep moving, staying in the molten phase, and bit by bit, all these impurities end up moving along with the ring, leaving behind a fairly pure material in its wake. This is so efficient that we now use it for refining a great deal of materials, but especially for silicon. Silicon, in fact, we just dangle it. You'll have a silicon rod. You'll have the ring. They're held on top by some clamps and on bottom. And the ring is narrow enough that the surface tension of the molten silicon is actually enough to keep it from flowing down this cylinder. So it will melt. There'll be a very thin line of melt, and that doesn't pop out. Just like water surface tension keeps stuff from overflowing, the silicon surface tension keeps it from overflowing. Particles that aren't supposed to be in there, the things that aren't silicon, will stay in the molten phase, and as this drifts down, it will solidify behind it. And bit by bit, it will push all the impurities down, where they will pile up on the bottom, leaving very pure silicon behind. So there's another form of purification methods. Other things, electro refinement. You can have a solution of your ions, run a current, and depending on your voltage you select, one of the things in solution may play out on your bar and the other won't. And so you can selectively remove certain ions from solution by controlling the refinement potential. There's a variety of methods at this point that we can use to purify materials. The need to isolate an element in its native pure form in the wild existed for most of human history and was very difficult. It is almost impossible to find iron as metallic iron on Earth because it oxidizes so readily. It is almost impossible to find copper as copper metal on Earth. Gold and silver, however, those weren't too difficult, which is why they probably were so popular in human history. They were the only metals that we really easily could just obtain from the planet. You could mine them straight out of a rock, heat them up, smash them, they'd take a new shape. We couldn't do that with almost anything else. This is also why it took us so long to fill in the periodic table. Removing these elements from the minerals and from the ores took a lot of experiment and time in order to find processes that worked, especially when we didn't even know if there was a new element in it to find. Let's a quick overview of the ideas and steps that go into turning a chunk of rock that you might find on the ground eventually into some of whatever element you're looking for.